Maldonado, and I'm a representative of the Heat Safe Engineering Firm, partnership with Southwest Research Institute and our mentor, Kyle Fernandez, in order to design and manufacture a heat resilient surveillance system, which is a camera that would sit inside a furnace and be able to record live footage and evidence of how a client's product will stand temperature at 2200 degrees Fahrenheit and withstand a test of up to 30 minutes in labs. As you can see from our key specifications, the maximum weight cannot exceed 45 pounds in weight. This is due to the fact that a lot of the engineers within the firm would have to maneuver and move this system around or conduct different testings throughout the lab, and it wouldn't be able to sit in one place. So if they exceeded that weight, a lot of people wouldn't be able to pick it up and it would make it difficult to transport. Also, our casing cannot exceed a 12 by 12 by 12 area, as our furnace only has a small square window that a camera can slide into. So if we exceed that, it wouldn't be able to fit. We make sure that we wanted to have a max area, so our heat transfer would take longer to reach steady state, and if a smaller one, it would take very little time. Also, our camera would have to be able to view it in the positive and negative direction of 45 degrees, as this would allow the camera to operate and record the whole square perimeter of the furnace and be able to film everything that's going on during the test. Okay, so as you see, our simulation, a lot of the hot points came from our glass, from where the camera looks at. This is because glass does not handle radiation well, and therefore a lot of what I had to do, and my sole purpose of the experiment was to provide heat and energy calculations to determine how fast our casing would reach steady temperature and how hot our camera enclosure would get. When first doing the experiments and first doing the testing, we initially started with a brass and copper kind of frame. With this, it was very costly, and it didn't really do so much better from our second material chosen, which is 330 stainless steel, which is a little cheaper and did almost the same exact thing. We also intended to provide a ceramic casing around the metal frame to help also insulate heat from reaching our inside enclosure. With that, we determined that our enclosure could withstand these temperatures, although the glass was still overheating exponentially. So in order to reduce that overheating, we decided to provide an air cooling tubing that would flow in between. We originally had 3 planes, but since now we're going to have an air cooling flowing between the 2 planes, we would have to only need 2 planes. And with this air flowing in between those 2 planes, it would provide substantial amount of cooling and, in result, keep our camera enclosure under 70 degrees Fahrenheit. That was the plan. When doing my calculations, I met with Dr. Montoyful as we advised, and we worked an energy calculation and a heat transfer formula that would help involve the heat coming from the furnace and how the heat attached to our metal enclosure and how the cooling would help subtract from that energy being forced into our system. During our calculations, I determined that, again, our materials would be able to handle the heat, although when it came to the glass, we still provide more cooling. So in future representations, we might even try to install water cooling or another form of cooling through our planes to help improve the heat transfer reductions within our system. And I would like to provide a special thanks to Kyle Fernandez, who helped fund and sponsor and mentor us in the right direction in order for us to succeed our goals. And I'd also like to thank Dr. Keith Axman, who also walked us through this whole semester and showed us what it meant to succeed in this design.